Hello everyone, welcome to this lecture in the Neural Networks from Scratch series. Today I am very excited because today we are going to learn about an optimizer which is used in most modern machine learning frameworks. If you are working in an industry or if you are working on a research project and if you have designed a neural network to solve any problem, the default optimizer which all engineers generally start with is the ADAM optimizer. In the previous lectures, we have looked at normal gradient descent, we have looked at momentum, and we have also looked at ADAGRAD and RMSProp. If you have not seen these lectures, I highly encourage you to go through them so that you will appreciate this lecture even more. I deliberately have constructed those previous lectures so that when we come to ADAM, your concepts will be clear because we will be using all of those building blocks while constructing the ADAM optimizer. If you have not seen the previous lectures, no problem at all. I've designed this lecture so that I'll go from the start to explain each and every step. My name is Dr. Raj Dandekar and I have a PhD in machine learning from Massachusetts Institute of Technology. I graduated with my PhD in 2022, and before that I graduated with a BTech in mechanical engineering from IIT Madras. So let's get started. Adam Optimizer was constructed in steps. So, a number of advances happened before researchers eventually reached the Adam Optimizer. And it's very useful as we learn machine learning to go through these advances sequentially. First came gradient descent. When there was a neural network, people realized that to optimize the weights and biases of the neural network, one of the best strategies is to move in the direction of the steepest descent so that we reach the minima of the loss function. And the direction of the steepest descent is given by negative of the gradient. Negative of the gradient. That's why people formulated the gradient descent procedure. So, whatever weights and biases which we have, you start with some random weight or bias, and then you keep on updating the weights or bias by moving in the direction of the steepest descent. That's why you subtract a learning rate multiplied by the partial derivative of the loss with respect to the weight or with respect to the bias. You keep on doing this iterative procedure for a large number of iterations, and then the hope is that you will eventually reach the minima, or you will minimize the loss function and the neural network will be optimized. So here you can see that there is a fixed step size. So whichever weight you are looking for, whichever bias you are looking for, all of the weights and biases have a fixed step size which is shared among all of them. That is the first feature of normal gradient descent. So this is the first feature. The second feature of the normal gradient descent is that to update the weights and the biases, only the current value of the gradient is used. So, for example, if you have reached the 50th iteration and you want to find the weight at the 51st iteration, then you take the weight at the 50th iteration and then you subtract alpha times the partial derivative of loss with respect to w at that current iteration, at the 51st iteration. And that is how you find the current value of the weights. So here you can see that only current gradient value is used and we do not give any importance to the past gradient values. So for example, you might be asking, what about the partial derivative of loss with respect to the weight for the first iteration, second iteration, 49th iteration? Don't they matter at all? And in normal gradient descent, the answer is no, they don't matter in normal gradient descent. People soon realize that normal gradient descent has a huge number of disadvantages. The first disadvantage is that we get stuck in a local minima. So let's say if the loss function landscape looks something like this, we there is a high tendency for normal gradient descent to get stuck in local minimas like this, and it's very difficult to discover the global minima. That's one of the biggest drawbacks of using normal gradient descent, and that's due to several reasons which people try to fix slowly. The first reason is the fixed step size and trying to make it more adaptive or more dynamic. The second reason, which is more predominant, is that why do we only use the current gradient value? for updating the weights. Why don't we use the past gradient values also? The past has a lot to teach us, so why don't we use it? That eventually led to momentum. The main idea of momentum in gradient descent is that the past gradients also matter. We definitely need to give importance to the past gradients. What this does is that if you give importance to the past gradients, oscillations reduce and we converge to the minima much faster. So, momentum is used to accelerate gradient descent. One way to think about this is that, let's say if the loss function landscape is something like this, and we start from here, right, and we want to reach the local minima, which let's say is here. Now ideally we should go in this kind of a manner, right, this kind of a straight kind of a line to the minima. But what happens is that if we use normal gradient descent, we will keep on moving in the direction of the negative gradient at that point, so that will lead to the zigzag oscillations like these. If you use momentum at a particular iteration for a particular weight, all the past weights are also given precedence. And when you give precedence to the past weights, the directions in left and the directions in right cancel each other out. And the only direction which survives is the direction in the vertically downward. So if we use momentum, it's more likely that we get this streamlined descent towards the minima and we reduce the oscillations. The way that this is represented in mathematical formula is that the new weight is the old weight minus step size multiplied by the partial derivative of loss with respect to w. This is the same as for normal gradient descent. The only difference is that we add this factor here. So we add a momentum factor multiplied by the previous weight updates. So here you can see in this term, the previous weights are also given a lot of importance, or rather I should say the previous gradient values are also given a lot of importance. The current gradient is not the only one which is used. This formula is also this same thing which I have written over here is also sometimes represented as this formula. The current weight is equal to the previous weight minus the learning rate multiplied by beta, which is the momentum factor and which controls how much weight is given to the past, multiplied by the current momentum value plus 1 minus beta times partial derivative of loss with respect to w. This is the current gradient. So it's this term which actually adds the weightage to the past values or the past values of the gradient. Um, to those who are familiar with more advanced mathematics, this term in the bracket is also sometimes called as the moving average. To those who are not familiar, it's completely fine. The way this term is represented, it actually means that we are giving a lot of importance to the past or the previous weight updates. That's the whole concept behind momentum, and it really does accelerate the convergence in a gradient descent by a huge factor. And it's routinely used in gradient descent. So momentum with gradient descent is much better than normal gradient descent. One problem with this method is that here again the step size is common and it's shared across all the parameters, right? But people soon started to wonder that why is the step size same for all the weights? So let's say if the loss function landscape looked something like this, right? Uh, and it's given by this function that w1 square by 100 plus w2 square. Let's say this is my loss function. Now you can see that even small changes in W1 will not lead to too much changes in the loss because there is a division of 100 here. But small changes in W2 will be now 100 times more powerful because it does not have the division factor. So shouldn't this mean that we should take larger step sizes for W1 and smaller step sizes for W2? Shouldn't we have adaptive gradients? The main idea of adaptive gradients is that smaller the gradient, higher is the step size. So for W1, the gradient is small because small changes in W1 lead to no changes in loss. So we should use higher step size for W1. Otherwise, W1 won't get updated at all. And for W2, the gradient is large. So we should use a smaller step size. So then people started thinking that this makes sense because if we don't use adaptive step sizes, then W1 will almost stagnate and not contribute anything, and only W2 will keep on changing in the iterations. So all the neurons which are associated with W1 will essentially become dead, and that would lead to the dead neuron problem where some neurons won't contribute at all. This is not good. So that led to the idea of adaptive gradients, where the main idea was that every weight should have a different step size, or an adaptive gradient rather, um, so that the step size effectively depends on the gradient value for that parameter. If the gradient value of the parameter is large, the step size will be small. If the gradient value of the parameter is small, the step size will be large. This led to the RMSProp method, where the update rule is given by this: the current weight is the old weight minus the learning rate multiplied by the partial derivative of loss with respect to W. Now, when I say learning rate, you can consider this whole thing as the learning rate. And you will see that if the denominator is not there, this just its normal gradient descent. But it's the denominator which makes the learning rate adaptive. Let's see how. The denominator is given by this formula: beta 2 multiplied by the cache value. So cache is equal to beta 2 multiplied by the cache plus 1 minus beta 2 into gradient square. So if you look at this formula here, over here, here we gave importance to the past gradients, right, while computing the momentum. Here you can see that it's a very similar formula, but we are giving importance to gradient square. And since this cache value comes in the denominator, higher the gradient, higher will this value be, and smaller will the effective step size. Smaller the gradient, higher will the cache value be, and smaller will be the, so higher the gradient, higher the cache value, smaller the step size. Smaller the gradient, smaller the cache value, and higher the step size. Now, the way the cache value is calculated is that we definitely give importance to the past gradient square also. So we don't just keep on accumulating the current gradient, we give importance to the past gradient square also. So whenever something like this is introduced where beta is there and 1 minus beta is there, it means that we are giving importance to the past. And instead of gradient, here we have gradient square. And instead of the beta 1 parameter here, we have the beta 2 parameter here. This beta 2 parameter is called as the cache memory decay rate, and it controls how much importance do we give to gradient square. So if we are at a particular parameter, okay, and we are wanting to update the parameter value at a current iteration, we first take into account all the gradient square values for that parameter. So we find partial derivative of loss with respect to the parameter whole square for all the previous values, and through that we compute the cache value. So if beta 2 value is very high, a lot of importance will be given to the previous gradient square parameters. And the reason it's gradient square is because we are using a square root here. So we are kind of effectively dividing by only the gradient. And the reason the epsilon parameter is added here is to prevent the denominator from becoming zero. So this thing which I have shown in the orange bracket here, it introduces the adaptive learning rate for each parameter. And that's the main idea of optimizers like RMSProp, or even optimizers like AdaGrad or AdaDelta. So here we can see that this is a bit different than momentum because we do not take into account the past gradients here. So here you see the current, only the current partial derivative of loss with respect to W is used. But we do take into account the past gradient square for finding these adaptive step sizes. So you should now appreciate the difference between momentum and RMS prop. In momentum, the past gradients matter, and they matter for finding the current gradient term. In RMSProp, the past gradient square matters, and they matter for finding the adaptive or effective step size. But in the current gradient, the only the current gradient is used, partial derivative of loss with respect to W. That's the difference between RMSProp and momentum. But both momentum and RMSProp are significant improvements to the normal gradient descent. The main idea behind the Adam optimizer is that what if we combine momentum with adaptive learning rates? Let me reframe this differently. Let's look at this particular formula here, right? We are using adaptive learning rates, but here we are only looking at the current gradient value, right? So the main idea of Adam is that what if this term, which is the current which is the partial derivative of loss with respect to weight in the current iteration, what if this term is replaced by this term which was used in the momentum? So what if this term was replaced with the momentum term? So instead of just using the current gradients, what if we replace this with the current momentum, so that we take into account all the past gradients into consideration? This will use the advantages of the momentum method, as well as it will use the advantages of the adaptive step sizes as introduced in the RMS prop. So it will kind of be the best of both worlds for us, and that is the main idea behind the adam optimizer. So what the adam optimizer says is that, the why don't we do this, why don't we say that the present weight is the old weight minus the learning rate multiplied by the momentum term. So instead of using the partial derivative of loss with respect to w, we use the momentum term here, as you can see, which gives importance to the past weights also, past gradients also, and then we divide by the square root of cash plus epsilon, which was exactly similar to what we did in RMSprop. Uh, so let me call this numerator term as momentum term, and let me call this cash over here as cash term. In the Adam optimizer, there is one small addition which is done. So what is done here is that sometimes this momentum term can start out with a very small value, so it might lead to the cold start problem for us, right? So we don't want that. We want the initial weights to make quick updates so that we explore the entire loss landscape. So for example, if the loss landscape looks like this, okay, and the initial weight updates are very small, we'll just keep getting stuck in this part, but there are a lot of other areas in the loss landscape to explore. So we want the initial weight updates to be quick so that we explore these other loss landscape also, other parts of the loss landscape also. So what we'll be doing is that we'll be dividing the momentum term by a correction factor called 1 minus beta 1 raised to t, and we'll be dividing the cash term by a correction factor called 1 minus beta 2 raised to t. Why this term? Because see, if t is very small, first you can see if t is very large, remember beta 1 is less than 1, so let's say beta 1 is 0.9. So if t is very large, it, let's say 0.9 raised to 50, this will almost be close to 0. So for higher iterations, it's like dividing. So this term will be 0. So it's like dividing by 1. So it will make no impact at all. But for lower iterations, let's say t is equal to 1, then this division term or this correction term will be 0.9 raised to 1, which is zero point 0.9. So 1 minus zero point 0.9 will be, so this term will be zero point 0.9, and 1 minus zero point 0.9 will be zero point 0.1. So we will be dividing the momentum term by zero point 0.1. So which will increase it by 10 times, right? Which will make sure that the weights are getting updated. Similarly, for the cash term, if beta 2 is equal to point, if beta 2 is equal to zero point 0.9, uh, if t is very high, this term will be approximately 0. So it will be like dividing by 1 and no changes at all if we are at higher number of iterations. But if we are at the iteration number 1, then this will again be zero point 0.9 raised to 1. So it will be 1 minus zero point 0.9, which will again be zero point 0.1. So then it will be dividing the cache term by zero point 0.1, which is multiplying it by 10 times. Again, that will ensure that the weight updates are happening in the initial iterations. Combining these two things, we ultimately get the final formula for the Adam optimizer weight updates. So W is equal to W minus alpha into momentum term divided by 1 minus beta 1 raised to t. This is the correction factor, divided by square root of cash term divided by 1 minus beta 2 raised to t. This is the correction term, plus epsilon. And epsilon is added just to make sure that the denominator does not become 0. That's it. If you look at the parameters in the Adam optimizer, there are generally two parameters, beta 1 and beta 2. Remember the origins of beta 1. Beta 1 controls the momentum term. So it defines how much importance is given to the past gradients in the gradient update. Whereas if you look at the cache term has beta 2, and beta 2 is called cache memory decay rate, and it controls how much importance is given to gradient square. So how much importance do we need to give to the past to adapt the learning rates? Generally in practice, beta 1 is taken to be around zero point 0.9, and beta 2 is taken to be around 0.999. Imagine this, beta 2 is 0.999, which means that when we calculate the cache term, we give tremendous amount of importance to the past gradients. So let's say if I am at a current iteration of a parameter and its past gradients are very high, even if its current gradient is low, I am going to use a small step size because I will give so much importance to the past gradients. So this is the ADAM optimizer, and as you can see, it builds upon two key concepts. The first key concept is that of momentum, and the second key concept is that of adaptive learning rate. And what is the adaptive learning rate? It's this term which I am right now marking in the orange color. You can think of this as the effective learning rate, whereas this term is the partial derivative or is the gradient term. So instead of just using the current gradient, we also give importance to the past, and that's the reason the ADAM optimizer has two parameters, beta 1 and beta 2. That's it. This is the simple explanation of ADAM optimizer and the origins of the ADAM optimizer in the first place. I hope you have understood up till this part and how we reached the ADAM optimizer, starting first from the gradient descent, then moving to the momentum, then moving to RMSProp, and then finally using all those building blocks to construct the ADAM optimizer. Now, in part 2 of this lecture, I want to actually take you through the practical demonstration of this. But before that, the first one thing I would like to clarify is that when I use alpha here, this alpha itself is not fixed, but it will be decaying with time. So generally, the decay is prescribed by alpha naught divided by 1. So let me show this rather than writing it again. Let me show it over here. So generally, the alpha is given by alpha naught divided by 1 plus decay into time, where this is the learning rate decay. So even the alpha, when I say it's not fixed, it's decreasing with time to make sure that the initial learning rates are high. All of this we are doing to make sure we don't have the cold start problem and the weights are not getting stagnated at the start. Okay, so in the part 2 of this lecture, I am going to implement the ADAM optimizer completely in Python, and I'm going to show you step by step how to code the ADAM optimizer and how to solve an entire neural network using the ADAM optimizer. So let us implement this in code. First, let me explain the problem statement to you. This is the data set which we have. If you look at the data set, every data point has two attributes, x1, or two features, x1 and x2. And if you look at any particular data point, let's say this, it belongs to either one of the three classes. It belongs to R, or G, or B. The goal for us is to train a neural network so that any new point, let's say if this new point is given to us, based on its values x1 and x2, we should be able to correctly classify whether it belongs to the red class, whether it belongs to the green class, or whether it belongs to the blue class. That's the problem which we have to solve, and this is a classification problem. So let's first see how the neural network architecture will look like. This is the neural network architecture which we are going to use, and this is the same one I'll be coding out today. So first, the data point has two input features, x1 and x2, and they'll be going through the first layer. So the first layer in this neural network has, let's say, 64 neurons, and then every neuron has a ReLU activation function connected to the output. After the output goes through the ReLU, it's passed to the second layer. In the second layer, there are just three neurons, and the output of these neurons is passed through the softmax. And then we'll get some output. For each input, we'll have three different outputs. So let's say if for the current x1, x2, the output is zero point 0.9, zero point 0.1, and 0. This clearly says that there is 90% probability that this point belongs to red class and 10% probability that this point belongs to green class. And based on these values, then we'll calculate the loss based on the actual data. So this is how we'll train the neural network to make the correct classification between red, green, or blue, and we'll be using the ADAM optimizer for it. So let me jump into code to show you how exactly this is done. So before we actually integrate the ADAM optimizer with the forward and backward pass of the neural network, we first need to define a class. and that class is called as optimizer adam. This class will have four methods. It will have the init method, the pre-update params, the update params, and then finally the post-update params. Let me explain each method step by step. So when we create an instance of the optimizer class, it will by default call this init method. Now we are keeping track of many things in this init method. So if you have understood this this formula, you will really understand what all different parameters I have. First, let me start from these parameters: beta 1, beta 2, and epsilon. Okay. So beta 1 is by default set to zero point 0.9, and remember, beta 1 is the momentum, how much momentum rate or how much importance is given to the past gradients. Beta 2 is the cache decay memory rate, and it governs how much importance is given to the gradient square in the adaptive learning rate. So by default, beta 1 is set to zero point 0.9 and beta 2 is set to 0.999. So these are the two parameters we track. We also track epsilon. Remember, epsilon is added to the denominator to make sure denominator is not 0, and it is typically a very small value, 1 into 10 raised to minus 7. Other parameters which we track all correspond to this alpha. Remember, this alpha term which is there is not constant, but we are going to use the adaptive learning rate, or rather the learning rate decay. So I'm just going to go to that part where, yes, so the alpha, for alpha we are going to be using the learning rate decay. So alpha is alpha naught divided by 1 plus decay into time, right? So we need to keep track of three things. We need to keep track of initial step size, the decay rate, and the iteration number, right? And these three things which we need to keep track of have been mentioned over here. So first is the initial learning rate, which is by default set to 0.01. Second is the decay rate, which is by default set to 0. And third, we also need to keep track of the number of iterations, because as you can see here, the learning rate also depends on the number of iterations, which is mentioned by t over here. That's the iteration number. So all of this we are keeping track in the init method. Then we come to pre-update params. So before we update the parameter values, we need to calculate this alpha, which is alpha naught divided by 1 plus decay into time. So this alpha is the one which has been mentioned over here, this alpha. So first we need to calculate this alpha, and that has been calculated in this pre-update params function, where the current learning rate, as I mentioned, is alpha divided by 1 plus decay into time. Then comes the most important method, where we are actually going to update the parameters. Okay, now I want you to focus on two things. First, in the code, or in the whiteboard rather, I always talked about weights, right? But the same thing will be done for the biases of the neural network as well. So in the update params method, you will see that there is the update rule for weights as well as biases. So I'm just going to focus on the weights here, and you can apply the same learning or the same logic to biases also. So there are two things which we need to keep track of. There is this numerator, which is the momentum term, and there is the denominator, which is the cache term, right? So for every weight and for every bias, we will have a momentum term in the numerator, and we will have a cache term in the denominator. So first we create empty matrices. So for the momentum term, it will have the same dimensions as the weights of the neural network, because every weight will have a momentum term associated with it. Similarly, the cache value has the same size as the number of weights in the neural network, because for every weight we are maintaining a cache. Remember, every weight has a different step size, right? So for every weight we are maintaining a cache value, and the same thing happens for bias also. Then what we are going to do is we are going to update the momentums. So if you look at the momentum which is mentioned over here, let's look at the momentum term. It's beta 1 into the previous momentum plus 1 minus beta 1 into the current gradient. So remember this formula: it's beta 1 into the previous momentums plus 1 minus beta into current gradients. So remember, layer, when we initiate a class of the layer, it has the backward method in it. So we are automatically storing the partial derivative of loss with respect to the weights and biases of that layer. Similarly, for bias, we do beta 1 into the past bias plus 1 minus beta 1 into the partial derivative of loss with respect to bias, which is the current gradient. And then we are going to employ the correction term. So remember that the momentum term is going to be divided by this 1 minus beta 1 raised to t. So in this part of the code, we are implementing the correction term. We take the momentum term and we divide by 1 minus beta 1 raised to t. For practical purposes, we have added 1 in the denominator so that the iterations don't start from 0 and we don't have a division by 0 over here. Or rather, we don't have starting from a very large value. I think that's why a plus 1 is added. So remember, this is beta 1 raised to t plus 1, right? It's not beta 1 multiplied by t, but it's 1 minus beta 1 raised to t plus 1. uh, you can also do it just with t, but I've seen that in all the codes it's always the plus 1 is added. I think it helps to give a better start to the initial weights and the biases. The similar thing is done for the bias correction term as well. And then finally, we look at the cache. So remember, the formula for the cache is that beta 2 into the previous cache plus 1 minus beta 2 into the current gradient square, right? So the weight cache is beta 2 into the previous cache plus 1 minus beta 2 into the current gradient square. Similarly, the bias cache is beta 2 into the prior bias cache plus 1 minus beta 2 into the current gradient of the bias whole square. Remember, when two star operators are put together in Python, it's actually the exponent or raised to. Then we get the corrected cache. So similar to the way we corrected the momentum in the numerator, in the denominator we will also need to correct the cache term, or we'll need to divide it by 1 minus beta 2 raised to t. So what we'll be doing is that for the weight cache and the bias cache, we'll be dividing the denominator by 1 minus beta 2 raised to t plus 1. Again, the plus 1 is added here, similar to for the momentum. For the bias also, we take the bias cache and divide by 1 minus beta 2 raised to t plus 1. Then that's it. Once we have calculated the numerator term, which is the modified momentum, and the denominator term, all we need to do is update the weights. So the new weight is the past weight minus alpha times the momentum divided by square root of cache plus epsilon. That's exactly what's done here. Weights, the current weights are the previous weights minus alpha times the corrected momentum divided by square root of the corrected cache plus epsilon. Similarly, for the biases, the current bias is equal to the past bias minus alpha times the momentum in the bias corrected divided by square root of bias cache corrected plus epsilon. So this is how then the weights and biases of every single layer of the neural network are updated according to the ADAM optimizer. And finally, it's very important to call the post update params. After we update the parameters, we need to increase the iterations, because remember that the next iteration step size depends on the number of iterations. Alpha is equal to alpha naught divided by 1 plus dk into t. So we definitely need to keep track on the number of iterations which we are on currently, and that's why we need to call the post update params. So now this is the adam optimizer class and I'm just going to run it. So okay, this has been run and now I am going to implement this class on the neural network. Please remember the neural network data set which we have. So this is called as spiral data. And please also remember the architecture. We are going to be using 64 neurons in the first layer, then ReLU, then 3 neurons in the output, then softmax, then the categorical cross entropy loss. So first we create the data set. We are using spiral data set here with 100 samples and it has 3 classes. It can belong to red, green or blue. Then we create the first layer. The first layer has 2 inputs and 64 neurons. We chain it with the ReLU activation function. Then we create the second layer, which has 3 neurons. Then we chain it with the softmax and the categorical cross entropy loss. This is exactly following the architecture which we have drawn on the whiteboard over here. Once we have written up till this part, we have to specify the optimizer. In the previous lectures, we have tested with SGD, ADAGRAD and RMSProp. In today's lecture, we are going to be using ADAM and the learning rate, which is the alpha naught, is 0.02, and the decay rate we are going to use is 10 raised to minus 5. All other parameters have already been predefined here, such as epsilon, beta, which is beta 1, which is zero point 0.9, and beta 2, which is 0.999. Great. Then we come to the forward pass and the backward pass. So we'll be doing 10,000 iterations of the forward pass and the backward pass. Remember that in each forward pass, we calculate the output of all layers of the neural network. In the backward pass, we find the partial derivative of the loss with respect to the weights, the inputs, and the biases of the neural network. And then we'll update the weights and biases of the neural network based on the optimizer, ADAM optimizer. So the first thing what we do is forward pass through the first layer, which is the forward pass through this first layer. So let me actually mark it with a different color. The first thing what we'll be doing is taking the forward pass through this layer, then going through the ReLU. So we take the forward pass through the first layer. The output of the first layer is fed as the input to the ReLU activation. Then we do the forward pass through the ReLU activation. The output of the ReLU is fed as an input to the next layer, which is the second layer. And then we calculate the softmax and the categorical cross entropy loss. So all these four statements up till here are the forward pass. In this part of the code, we are just printing out the epoch number, the accuracy, the loss at every epoch. And remember, the learning rate is adapting. So the learning rate is changing with each epoch. So that also we are printing it out. One epoch is just going through the data set entirely once. So keep that in mind. And then we will be running the backward pass. So first we will find the partial derivative of the loss with respect to the softmax input. Then we'll find the partial derivative of the loss with respect to the weights and biases of the second layer. Then we will find the partial derivative of the loss with respect to ReLU input. And finally, we'll find the partial derivative of the loss with respect to the weights and biases of the first layer. Once we have found all the partial derivatives of the loss, we are ready to call the different optimizer methods which we have defined over here. So first we are going to call the pre-update params, which will make sure that the learning rate is updated. Then we are going to call the update params, which will make sure that the weights and biases of every layer are updated according to the current partial derivatives of the loss with respect to those weights and biases. And then we will call post update params just to increase the iteration number and to keep track of the iterations. So we call pre-update params, then we call update params for the layer 1, and we call update params for layer 2, because the parameters of both these layers need to be updated. And then we call the post update params to make sure that then we call post update params to make sure that the iteration number is updated so that the learning rate in the next iteration can be adapted accordingly. So this is how the entire forward and backward pass code is written with the ADAM optimizer class. And I'm going to run this code now to see the outputs. So let's see the outputs here. We can see that we are running 10,000 epochs. So you can see 10,000 epochs has been run, and let's see the final accuracy. It's 0.957 and the loss is 0.099. So let me note down this accuracy here, which is for the ADAM optimizer, we got the final accuracy as 0.957, right? Which is amazing. And here you can see that the loss has decreased to 0.099. If you have followed the previous lectures, you will see that this is the best accuracy which we have got so far. But now we can test out different accuracies, right? So first I am going to test out the accuracy with just the let's say if I test it out with RMSProp. So if I test it out with RMSProp and then just run it. So remember that RMSProp just uses the cache value and it does not take into account the momentum term in the in the numerator. And the RMSProp is now running, and right now I'm at around 3000 epochs, and here you can see that the accuracy is still 0.63. Let's see how much the accuracy is when we reach around 10,000 epochs. So now I am at epoch number 7600. Okay, finally I'm at 9000 epochs, and now you can see that 10,000 epochs have been completed and the accuracy is 0.717. So for RMS prop, the accuracy is 0.717. which is nowhere compared to the Adam optimizer accuracy which we obtained. Now let us try to see the accuracy for just the stochastic gradient descent with momentum. So this is with momentum, but we are not using the adaptive step sizes like which are used in RMSProp and Adam. So let's run this right now. Okay, so as you can see, I'm running the SGD or the gradient descent with momentum rather, which just uses the momentum term in the in the numerator, but it does not use the cache term in the denominator. So here you can see that we are getting a better accuracy, which is good, and the accuracy will reach to around zero point 0.9, I think. So we are at around 10,000 iterations, and the accuracy is 0.873. So I'll just write, just using the momentum, the accuracy is 0.873. Sometimes when you run different iterations, you will see that the momentum accuracy is as high as Adam. So momentum is good, but for all other problems of neural networks and machine learning, the Adam optimizer is the best optimizer to get started with, because it takes into account the momentum, plus it takes into account the adaptive learning rate or the cache term which is used in RMSprop. This is amazing, right? Now I just want to take you through some videos to show you the difference between the Adam optimizer, convergence, and the other optimizers. So first, let me just show you if we just use a decaying learning rate. And here we are not even using momentum. We are not even using the cache term in the denominator. This is just a decaying learning rate. So here you can see that the iterations will start now. Okay, here you can see that the iterations have started, and if you see the background colors, they are the predictions. They should ideally match the true data colors which we have. uh, so now if you can see, this is the final prediction if we just use a decaying learning rate without momentum or without the RMSprop. Here you can see it's pretty bad, right, with respect to prediction, because if you see these points over here, our prediction, which is the blue background, that's our prediction, but these two are green, so they are misclassified. If you take these points here, they are in a green background, so these red points are misclassified. So it's not very good. Now let's look at the RMSprop. The RMSprop optimizer does not use momentum, but it uses the cache term in the denominator, and it does a slightly better job. So here you can see that it's kind of looking like a spiral now. It's not exactly looking like a spiral, the outside color. It's definitely doing a better job than just using the decay rate without momentum or without the cache term in the denominator. So here also you can see that there are a number of misclassifications. These green points over here are misclassified as blue. Then this blue point here is misclassified as red, etc. So it's not the best. Now let's look at Adam. So I'm going to be running the Adam optimizer now. So here you can see right from the start, the Adam optimizer leads to amazing results. Here you can see that the if you look at the backgrounds, they look like spirals. So this is the final result given by the Adam optimizer, and you can see that almost all points have been classified correctly. There are very few misclassified points. The border colors which we have look like spirals, which match the colors of the data points. This is brilliant, right? This clearly shows that the Adam optimizer is probably the most robust optimizers among the different ones which we have tested. Okay, so thank you so much everyone for attending this lecture or for listening to this lecture. I tried to explain Adam right from the basics, and I tried to motivate the concept of Adam through first showing you momentum, then showing you gradient descent, then showing you the cache term, and then showing you how all of these three tools. So first we have the normal gradient descent, then we have momentum, then we have the cache term, and then showing you how all of these contribute together to lead to the Adam optimizer. So the Adam is just a culmination of these building blocks which people had worked on previously, but it turns out to be the best and most robust optimizers which is used in many machine learning settings. Remember that the Adam has two parameters which are most important: the beta one, generally taken to be around zero point 0.9, which is the momentum factor, and the beta 2, which is the cache memory decay rate, or the adaptive, or the rate which controls how much importance is given to the gradient square or the past gradient square values to make the adaptive step sizes. And then we looked at the Adam optimizer in code. We saw how the Adam optimizer class was created and how it was integrated. with the forward pass and the backward pass. I hope you are deriving a lot of value from these lectures. When I was taught ADAM for the first time, I did not really understand it at all. But I realized that you need to break it down into different small concepts, and when you put them all together, it's quite easy to understand. I really encourage you to write all of the steps which I am describing here and to also replicate the codes which I am providing. Thank you so much, everyone, and I'll see you in the next lecture.